Hello bro, back with me, Rannegoro. We are going to discuss about some classical mechanics questions or problem at the undergraduate level. Problems that we will discuss is related to Newton's second law with a differential equation approach. Okay, prepare yourself to enter the world of classical mechanics. First problem. A particle of mass m is subject to a force F as a function of V equals minus B V square. The initial position is 0 and the initial speed is VO. Find x as a function of t. Okay, we can solve this problem using Newton's second law. Okay, first writing it as F equals MA, that gives B V square equals m dv dt. In separating variables and integrating gives integral from O to t dt equals integral VO to V 1 divided by V square dv, and then we get minus b t m from 0 to t equals minus 1 divided by V from VO until V, and BT divided by M equals V substituted by V and VO. We get VO minus V. Okay, and we can writing it as 1 divided by V equals BT divided by M plus VO. Okay, like that. Solving for V, writing it as dv dt, and then separating variables and integrating gives that V, where V is dx dt, and then integral from 0 to x dx equals integral from 0 to t v dt, and then we substitute V on the right side by 1 divided by bt m plus 1 vo dt. We get from integral x m divided by b ln bt m plus 1 vo from 0 to t. Writing x again, x equals m b, we substitute t from 0 to t, and we get ln bt m plus 1 vo minus ln 1 vo. So mb ln bt m plus 1 vo divided by 1 vo. So we get x equals m b ln vt vo divided by m plus 1. That's the solution to the first problem. X as a function of t equals m divided by b ln bt vo divided by m plus 1. So let's move on to the second problem. A particle of mass m is subject to a force F as a function of x equals kx, with k is greater than 0. The initial position is xo and the initial speed is 0. Find x as a function of t. Okay, again, we can solve this problem using Newton's second law. First, writing it as F equals ma, and substitute F by kx equals m times a, and we write a as dv dt. By chain rules, we can substitute the dv dt. dv dt equals dv dx dx dt. dx dt is equals v, So we can write dv dt equals v dv dx. Writing it again, kx equals m v dv dx. And separating variables and integrating it, and we get integral from xo to x kx dx equals integral from o to v m v dv. We get on the left side 1/2 k x to the 2 minus xo to the 2 equals 1/2 mv square. Solving for v, writing it as dx dt, and then spreading variables and integrating, we get 1/2 mv square equals 1/2 k x square minus xo square. We eliminate this, and v square equals k divided by m x square minus xo square, and we get v equals square root of k divided by m x square minus xo square. And we can writing v as dx dt equals m x square minus xo square. Go to the next slide, and we write the integral from x0 to the x1 divided by square root of x square minus xo square dx equals integral from 0 to t square root of k divided by m dt. And we can using substitution, and we solve the left side by hyperbolic function. Cos hyperbolic square sin hyperbolic square equals 1. This is the property of hyperbolic equation. We move sin hyperbolic square, and we can rewrite this as 1 plus sin hyperbolic square equals cos hyperbolic square times xo square, and we get xo square plus xo square sin hyperbolic square equals xo square cos hyperbolic square u. And we move this from the left side to right side, and we get xo square sin hyperbolic square u equals xo square cos hyperbolic square u minus xo square. Let x equals x0 cos hyperbolic u, and u as inverse of cos hyperbolic x divided by x or x0, and we get xo square sin hyperbolic u equals x square minus xo square. We substitute this as a x. We take a square of root, then write it again. Xo square sin hyperbolic square u equals x square minus xo square, and we remove the square of this side like this. Xo sin hyperbolic u equals square root of x square minus xo square. Go to the next slide, and we can write dx du equals xo sin hyperbolic u, and dx equals xo sin hyperbolic u du. When x equals xo, u1 equals 0. We can substitute x in this equation, so we get u1 equals 0. And when x equals x, u2 equals u. Integrating it from xo until x1 divided by square root of x square minus xo square dx. On the right side is integral from 0 to u. We substitute this point by this term xo sin hyperbolic u du xo sin hyperbolic u. So we get u as a function of t. U equals plus minus square root of km times t, and we write the x in terms of u xo cos hyperbolic u, and substitute it by it. X equals xo cos hyperbolic square root of k divided by m times t. So this is the solution of second problem. Let's move on to the third problem. A chain with length L is held stretched out on a frictionless horizontal table with a length y0 hanging down through a hole in the table. The chain is released as a function of time. Find the length that hangs down through the hole, then bother with t after the chain lost contact with the table. Also find the speed of the chain right when it lost contact with the table. Okay, let the density of a chain be rho and let y as a function of t be the length hanging down through the whole time. Y as a function of t. Then the total mass is the implication of the density. The mass equals rho L, and the mass hanging below the hole is rho hanging below equals rho y. The net downward force on the chain is rho yg. So we can solve this problem using Newton's second law again. We write F equals m times a and gives this term of F as a mg equals ma. We can substitute mg by rho gy equals ma and rewrite m as a rho l on the right side, and we write a y double dot, and we can write y double dot equals g divided by l times y. We save it. At this point, there are two ways we can proceed. The first method, since we have of a function whose second derivative of proportional to itself, a good bet for the solution is an exponential function. And indeed, a quick check shows that the solution is y double dot equals g divided by l times y, and y double dot minus g divided by l times y equals 0. We can write it like this. The coefficient of this term, a equals 1, b equals 0, and c equals minus divided by l. And we can rewrite the equation as alpha square minus 0 plus minus g divided by l equals 0. So the alpha equals square root of g divided by l. The solution of the derivative equation of this is y as a function of t equals a exponential alpha t plus b a, like this. And this is a position as a function of t, so velocity as a function of t equals alpha a, like this. At the t equals 0, we can get velocity is 0. So from this term we can get equation that a equals b, like this. So at t equals 0, the position is y0, and we can write this term on the right side as a plus b equals y0, and 2 times a equals y0, and a equals b equals y0 divided by 2. Go to the next slide. So the length that hangs below the hole is y as a function of t, y0 divided by 2, a to the alpha t plus a to the minus alpha t equals y0 cos hyperbolic alpha t. This term is hyperbolic cos hyperbolic, and the speed is y dot t alpha y0 divided by 2 a alpha t e to the minus alpha t equals alpha y0 sin hyperbolic alpha t. This is a solution of the position of the time as a function of time, and the velocity as a function of the time. The time t that satisfies y t is L is given by L y0 cos hyperbolic alpha t. Using sin x equals square root of cos hyperbolic square x minus 1 from the properties of hyperbolic equation, we find that the speed of the chain right when it lost contact with the table is y dot as a function of t alpha y0 sin hyperbolic alpha t equals alpha y0 square root of cos hyperbolic square x minus 1 equals alpha y0 square root of y divided by y0 square minus 1. Sorry, this is L. Go to the next slide and we write again y dot as a function of t when t is t. So y dot t equals y0 square root of L square y0 square minus y0 square y0 square. We change the denominator of this side, this term. So the velocity equals alpha y0, and we can get 1 divided by y0 from this term, and square root of L square minus y0 square, and we can remove this, and y dot as a function of t, y dot t equals alpha square root of L square minus y0 square, where gamma 0 equals y0 divided by L. So we get the term of y dot t equals g divided by L square minus y0 square, and we can remove the term of L square, so we get g times L and 1 minus y0 square divided by L square. So the term of velocity at the time of t is square of gl, square root of gl times square root of 1 minus gamma square, and we get condition when gamma equals 0, the speed y dot equals square root of gl. This quickly follows from conservation of energy, like the speed of free fall. Okay, let's move to second method. We can write the acceleration y double dot as a dv dt, and with the chain rules we can write dv dt is equals to v, and we write p dv dy, and then separate variables and integrate to obtain the velocity and the position. So from Newton's second law, so y double dot equals g divided by L y, and we substitute it by alpha square, so y double dot alpha square y, and rewrite the term of velocity as v dv dy, and integrated it by integral from 0 to v dv equals alpha square from y0 to y dy, and we get v square divided by 2 equals alpha square y o square times 1/2. So v square equals alpha square y square minus y0 square, and the term of v by dv by dy dt equals square of alpha square times y square minus yo square. So we can integrate it again y, and we move this term on the right side from the right side to the left side like this, and the right side is alpha integral from 0 to t dt. Go to the next slide. We write again the integral. So the term on the left side is identical previous term, so we can write the solution of this term as u as a function inverse of cos hyperbolic, and the position is y0 cos hyperbolic u. So we arrive at y as a function of time equals y0 cos hyperbolic alpha t, and we get v or velocity y dot as a function of t alpha times square root of L square minus y0 square is same value with the first method. That's the solution of the third problem. Let's move on to the fourth problem. A beach ball is thrown upward with initial speed VO. Assume that the drag force from the air is Fg equals minus m alpha v. What is the speed of the ball Vf right before it hits the ground? An implicit equation is sufficient. Does the ball spend more time or less time in the air than it would if it were thrown in a vacuum? Okay, we can draw the free body diagram when VO is upward, so the weight is minus mg, and the drag force is same, is downward ft. So there are two forces that act to the object, to the beach ball, on both the way up and the way down. The total force on the ball is F equals minus mg minus m alpha v. That m alpha v is Fd, drag force from the air. On the way up, v is positive, so the drag force points downward as it should. And on the way down, v is negative, so the drag force points upward. Our strategy for finding Vf final velocity, the final speed of the ball, will be to produce two different expressions for the maximum height h and then equate them. We will find these two expressions by considering the upward and then the downward motion of the ball. In doing so, we will need to write the acceleration of the ball as a equals dv dt. With the chain rule, we get dv dy dt. This is the term equals v, so v dv per dy, dv divided by dv dy. For the upward motion, this Newton's second law, F equals ma, give F equals ma, where F is minus mg minus m alpha v equals mv dv dy, and we can integrate it on the left side. Integral from 0 to h dy equals integral from v0 to 0, v divided by minus g plus alpha v. It's from this term dv, where we have taken advantage of the fact that the speed of the ball at the top is 0, writing v divided by g plus alpha v. This is the fact. Okay, so we must change this term and we can integrate it as simple as the common. We change this term so we can simplify the integrate process. Let v divided by g plus alpha v times alpha, and we get v alpha divided by alpha times g plus alpha v, and we take out the alpha on the denominator, so 1 alpha, and we give some change g minus g plus alpha v. So this is value is 0 divided by g plus alpha v, and we get on the right side 1 alpha g plus alpha v per g plus alpha v. We separate it with the same denominator g plus v, and we get the term of v divided by g plus alpha v equals 1 divided by alpha 1 g divided by g plus v. So the integral from 0 to h dy equals minus integral from v0 to 0, v divided by g plus alpha v dv. We change this term and we get on the left side is h equals on the right side minus 1 alpha integral from v0 to 0, 1 minus g divided by g plus alpha v dv. And then we get from integral process h equals minus 1 divided by alpha v plus g ln 1 divided by g plus alpha v times 1 alpha from vo to, and we substitute this term dv by vo and 0. So we get h equals minus 1 alpha minus vo plus g ln g plus alpha o divided by g times 1 alpha, and we simplify this term, so we get 1 alpha minus vo plus g ln 1 plus alpha vo divided by g times 1 alpha, and finally we get h is vo divided by alpha g alpha square ln 1 plus alpha vo g. This is the height of the beach ball as a function of alpha. Let's go to the next slide. Now consider the downward motion. Let Vf be the final speed, which is a positive quantity. The final velocity is the negative quantity minus Vf. Using F ma, we obtain minus mg minus m alpha v equals m. We substitute a by v dv dt dy and remove m and integrate it. On the left side is integral from h to 0 dy equals minus integral from 0 to minus vf. V divided by g plus alpha v. And the left side is minus h equals minus 1 alpha integral from 0 to minus vf. With the same process, we can change this term with 1 minus g divided by g alpha v dv. So the right side is minus 1 alpha v plus g ln 1 divided by g plus alpha v times 1 alpha from 0 to minus vf, and we substitute the f by 0 and minus vf, and we get h equals 1 alpha. We remove this sign, minus sign, 1 alpha times in bracket minus vf plus g divided by alpha times ln g alpha divided by g minus alpha vf. So we can get h as minus vf divided by alpha minus g alpha square ln. We can switch denominator and numerator place g minus alpha vf. So the implication is this term has a minus sign. G minus alpha vf divided by g alpha, and we can change this term like this: g alpha square ln 1 minus alpha vf divided by g. Okay, this is the expression of h that has alpha. Equating the expression for h first term and second term, this is a second term and this is a first term, and gives an implicit equation for vf in terms of vo. So h and h in first and second equation, rewrite vo divided by alpha minus g divided by alpha square ln 1 plus alpha vo divided by g equals, in the second equation, the right side is minus vf divided by 2 divided by alpha, and minus g divided by alpha square times ln 1 minus alpha vf divided by g. And we can move from this term from right side to left side. We can multiply all of term with alpha. So the left term is vo and vf plus vf, and the right side is g alpha. This is right in the bracket ln 1 plus alpha vo divided by g minus ln 1 minus alpha vf divided by g. And we can simplify this equation by integrate this term ln g divided by alpha in the bracket ln with the same denominator. On this side is g plus alpha vo divided by g divided by g minus alpha vo divided by g. So vo plus vf equals g divided by alpha ln, we can remove this, g plus alpha vo divided by g minus alpha vo. This is the velocity equation in terms of alpha, and we can answer the question: does the ball spend more time or less time in the air, and it would if it were thrown in a vacuum? So you can solve it by this term that we get from Newton's second law. More or less like that, the use of different equation to solve problem lead to Newton's second law. We can develop and apply it to other cases. Thank you for your attention. Please, you can comment below if my delivery is not appropriate. Thank you again. See you soon. Salam untuk kawanku.